So my name is Carolina Mora Lopez. I'm representing here the engineering team at imec. I'm at the moment leading a team of engineers that are busy with the development of these Neuropixels probes. The team has grown quite significantly since the very start. I think at the beginning was mostly me alone, but at the moment the team is pretty large from the design side. Of course, many other teams are busy at imec with also fabrication, testing, packaging, but let's say I'm representing the part of the probe design. What is imec? So imec is a research institute. Is very strong in the world for semiconductors. What we are trying to do is innovation. So imec is kind of a mixture between an academic lab and industry. So it's something in between. It's a company that is looking to perform innovation and research from semiconductor perspective, but of course having all the cool technology that industry can provide. So imec is a pretty large organization. We have the headquarters in Leuven, Belgium. There are other 7 sites around the world, with the second biggest is in the Netherlands. So Belgium and Netherlands are the 2 largest hubs where all the developments and research happens. We have more than 4,500 employees, including also PhD researchers, and we have a pretty large infrastructure for the development of all sorts of semiconductors, devices and applications. And and because of this infrastructure, we also can collaborate with many industrial partners and academic partners to develop, let's say, new applications and new devices such as the Neuropixels probes. I will not go very much in detail, but what makes imec special is the infrastructure. So we have 2 very large clean rooms that can be used to build, for example, things like nanopores, nanochannels, photonics, electrodes, all things on demand. And this can be combined with CMOS, that is electrical design on silicon. And then this can serve many applications, not only from the bio side or the biomedical side, like the probes, but also other things related to RF or imagers. And that's what I explained here in this slide. So we don't only work on the part of what we call smart health, but there are many other applications that imec is busy with. So that was an imec introduction. From now on, I will just start talking about our probes. So what motivates us to start developing Neuropixels is the need for having a tool that can interrogate the brain at a much larger density. So we have seen a very rapid development of tools that can perform neural recording in the last decades. They have become more functional, more compact, and cheaper, but we were still very limited by the amount of neurons that we can record at the same time. So we came up with the idea, I think it was 10 years ago or more, to try to combine the silicon probe together with electronics on the same device. And this will, of course, tackle the bottleneck of the wiring. I will explain that later, and will bring much more functionality to the probe and make the recordings much more robust. So what is inside a CMOS probe? So this is Neuropixels 1 device. So it basically has an array of electrodes that is covering the whole implantable shank or needle. These electrodes are selectable, and you can combine or select pseudo-random combinations of these pixels that will be recorded by an electronics that is in the base, and the purpose is to convert this to digital domain. So we have an analog input, but a digital output. And this is special because it makes the recordings more robust against noise and interferences. So this is what happens in the probe. So basically, you select the site, the signal will be recorded and will travel through the shank to a first amplification stage. This amplification then will make your signal larger with a fixed gain. And this signal will be split in the AP components and the LFP components separately. You can apply also different gains for both, and they get combined into an analog to digital converter, and the data is pushed out to the head stage. So this is the whole process that happens in the probe. I will show very briefly, but this is of course very technical from the electronic part. I will show what is inside. So basically we have then the array of electrodes with around 1,000 pixels. What we call pixel is just the circuit that is beneath the electrode. What is beneath is a switch and a local memory that you can program to say, okay, I want this switch closed or open for selection. What is in the base is, as I showed in the previous slide, is an array of channels. A channel is then what takes care of the recording. So we have an amplification stage. We have a band separation filter for AP and LFP. We have programmable gains that are independent for both bands. And then this is a multiplex and given to an ADC. So what was important about the design are electrical specifications such as noise. So we needed to achieve low noise with the very small electronics. This is actually quite challenging. The smallest you go in design, the most difficult is to achieve a good noise performance. So there is always a trade-off between area, noise, and power consumption in a CMOS design. And we have here a 10-bit resolution ADC, and sampling rates are 2.5 kilohertz for the LFP and 30 kilohertz for the AP. There is also a publication that has more details on the electronic side if someone is interested on the CMOS design, so you can check out. So for the channel, I explained already that the two bands are separated in two. This only applies for Neuropixels 1, by the way. So in Neuropixels 2, this band separation is not present anymore, and we record the full band. I think for next year course, probably if the 2.0 probes will be already out, it makes sense to also explain how that works. But here, the band gets split between 300 hertz to 10K for the AP and 0.5 hertz to 1 kilohertz for LFP. And each of these bands can have programmable gains. So what the Neuropixels probe is trying to solve is basically this shank wiring bottleneck. So as you know, in a passive probe, basically, the number of electrodes that you accommodate in a given shank width is really limited by the number of wires that you can pass through that shank. The only way to pass that limit, a part of adding more metallization levels, is to use switching. So when you add switching, you can basically cover the whole chunk full of electrodes while having a limited number of lines. And then these lines, signal lines, will be shared among all the electrodes, and you can decide which electrode you want to connect to a certain line. Of course, there are some limitations. And here I'm trying to explain what kind of selectivity you can do briefly. So you can either select groups of 384 consecutive electrodes, and this window can be moved by one electrode. So you can basically shift this window to any group of 384 that you want all along the shank. You can also select subgroups of consecutive, so you can spread them along the 3 main groups. So something important to understand is in these probes we have like 3 subsets of groups that are sharing the same channel. So the electrode number 1 from this group is sharing the same channel as electrode number 1 here, meaning that these 2 cannot be selected at the same time. But you can still select groups that are not overlapping and spread them. You can also select individual electrodes completely spread as long as you don't overlap the common channels. So we also have the options for reference selection. So referencing is very important for the experiments that you want to do, because this will determine also the type of signal to noise ratio, and it will determine a lot how much noise you get or how many artifacts. So basically we have 3 options here. The probes include a very large tip electrodes that can be used as a reference. We have a few small electrodes as well that can be selected. This, however, since the electrodes are very high impedance, the cancellation is not super great if you want to use only one electrode as reference for all the channels. So it's very high impedance to drive too many channels at the same time. And we have the possibility to connect an external electrode as well. So basically each channel can select which of the 3 references to use. And in software you can use then this selectivity to establish which reference to assign to each channel. Normally in practice, you select the same reference for all channels. I haven't seen any practical reason why you would do differently. So I want to spend a bit of time explaining the difference between reference and ground. I think this is a common question, and I also receive still by email quite some questions from users about what is the best approach for referencing and ground. So I wanted to explain this difference. So basically what we call ground is a voltage reference that it will help you to establish what is the observation range of your amplifier. So your amplifier has a ground that for us is like, let's say, the 0 volt reference. And we need to make sure that the animal is also referenced to this ground to make sure that the signal that you observe is within a certain limit that the amplifier can observe. So if you don't ground your animal, so if you leave it floating, the signal that you will record will be centered around a voltage that we call V-float, whatever voltage it is. And this voltage is something that you cannot control. So it's something that the animal will be having depending on the location, on what is touching. So it is possible that this signal will not fall within the observation range of your amplifier. So it is important that the animal is grounded to the same reference as the probe or the head stage of the system to make sure that the signal is really within the limit. So it will be centered exactly where the amplifier is expecting an input. So this is the ground. The reference is something different. So the reference is a reference signal against which you want to do your differential amplification. So if you have common noise in your reference and in your input, basically you will have a good cancellation of your common mode noise and only record the signal that matters. So what happens very often is that you use your amplifier as single-ended amplification. Single-ended means that you are connecting your reference to ground, so to a quiet voltage. But then what happens is that any signal that couples to your signal electrode will also be amplified at the output. So you will be basically having a very common mode rejection, and this may affect your experiments depending on how noisy your setup is or your lab. So I will explain 3 grounding reference schemes that you can use. So the first one is, as here, using two different electrodes, one for grounding and one for reference, that are external. This can be quite versatile. Problem is that you will need two external electrodes, but you can achieve a good common mode cancellation, depending on how long these cables are, of course, and how much movement the animal will have. But this can be a good way of doing the grounding and reference. I think this is a common approach among all the users, and is really short the reference and ground in the flex PCB, and connecting only one ground to the animal. An advantage is you only require one wire, so I think that the setup is a bit simplified and is very user-friendly, but you will have here poor cancellation. So here you really need to take care that the environment in which the animal is quiet, and yeah, either you use a Faraday cage or other means to keep your setup clean of noise. And the last one is the internal reference. So I think this is one of the best options, because first you only need one wire, plus you will also have good cancellation because you have an electrode that is in the same environment. I also believe this will be the best for movement artifacts, because the reference electrode and the signal electrode will move together at the same time. So these are the three approaches. Of course, if one of these approaches works in one lab, doesn't mean that it will work in another. So always you need to look specifically at your lab conditions to see what the problems are. And I think this is one of the main issues that you can encounter when trying to build your setup. So yeah, always something that unfortunately is a bit trial and error, but here you have the options that you can try. Okay, so I will explain a bit about the probe fabrication. So I explained already the design, so what is inside the probes, but the fabrication happens using both CMOS technology and imec technology. So the CMOS is just a standard CMOS technology. It's 0.13 micrometers technology. This gets fabricated outside imec, and we use later the wafers in our clean room to fabricate the electrodes and also the shapes of the probes. So this is how a device looks when you have some close-up pictures. So you have the shank that is 24 micrometers thick and have this array of electrodes somehow like in zigzag. The electrodes are 12 by 12 micrometer. They are made out of titanium nitride. This is a very low impedance electrode and also biocompatible. So it's very good recording material. We design our probes to have a thick base. So this is a very special fabrication that uses a special technology. It's called SOI that allows to have different in thickness. And this is important for us because we need to handle the probes. We need to be able to take the probes, package them. And this is a way to prevent that the probes are too fragile to be handled during packaging and testing. So why do we use CMOS technology? So actually this is the dominant integrated circuit fabrication technology, and it uses many types of processes such as film deposition, patterning, and semiconductor doping. The reason why we use CMOS is that it allows to have, they say, active devices such as transistors, but also very a good stack of metals. It can go up to 9 metals depending on the technology, even more. And you can have features down to 5 nanometers in some of the technologies. So you can really pack a lot of transistors and active devices in a very small area. And a part of that, it gives a lot of reliability. You can achieve low power consumption. If you use it in volume, it can be low cost, and it can be very easily scalable in a process. So if you really want to develop many devices, then this is the way to go. I wanted also to mention some downsides of the technology. So when you design an amplifier or any type of device in silicon, you will always have something that we call process variation, because the sizes are so small. Some of the parameters are not always reproducible in the exact way. Although it's very well controlled, you will always have a small variations due to the very small sizes. And the smaller you go, the more variation you will get. So let's say, as an example, a capacitor in CMOS will look like this. It's a stack of a metal, an insulator, and a metal. And ideally, it will the layers will look very straight, but what can happen is that you can have difference in thickness, and I say the position of these layers is not very uniform, so you will get certain roughness in the surface. So what you will end up is with a capacitor that has a variation, let's say, of plus minus 20%. And this make the performance to vary in electronic circuit. So it can be that, for example, the gain of the amplifier can vary by a certain percentage, or that the bandwidth or that the noise is different. And in some cases, when the process variations, because this is a statistics, of course, there will always be a device once in a while that doesn't work properly or even not at all. So this specifically for the probes we have, this will create gain bandwidths and ADC inaccuracies. So how do we deal with this with the Neuropixels probe? So we have implemented some ways to calibrate the probe. Probe calibration is meant to correct for 3 things. One is the missing codes of the analog to digital converters, to correct for any gain errors or any offset, large offsets. When we talk about calibration, this is not signal processing. So this is really something that gets adjusted in the electronics, in the hardware, to compensate for certain variations. What we do at IMEC is that we measure every single probe that is fabricated. We analyze the parameters, and we will provide together with the probe certain calibration files that you need to program to the probe to fix any imperfection that it can have. So it can be also that the calibration is not sufficient to fix certain probes. If the probe, of course, is very bad, we will never put it on the market. That's not what we will do, but it may have some channels or that are maybe more noisy probes that you can get. So it's important that this calibration is always applied. So although it's an option, you will receive the file and it's up to you if you use it or not. We really encourage you to calibrate your probes. I believe all the softwares that are now available are taking into account those files. So yeah, I think it should be a little step that you need to do before every experiment to apply this calibration. I want to just close my talk showing the whole system. So of course the probe is by itself is completely useless if you don't have a good acquisition system. So the Neuropixels probes comes as well with a head stage that basically gathering the digital data from the probe and converting it to a serial interface that can go to the computer. So if you have here the probe, there is a head stage, and then you have a cable, can be up to 5 meters, that will go to the PXI acquisition module. I think that will be explained later in other talks. You can connect several probes to up to 4 into one module, and you can have also several modules into the PXI chassis. So you can have, I think, I don't know how many has been demonstrated till now, but I know up to 16 has been tried. But yeah, so you can really have a lot of recording, and each probe has its own channel. So you have 384 per probe, and you can multiply that by the number of devices that you connect here. So there is the website for the user manual. You have more information about details of the electronics, how to use it. There is also a paper on the full data acquisition system if you want to know more details as well. So thank you for your time.
Thank you so much, Carolina. There's lots of questions, and I think we're going to get to only a couple of them.
Yeah.
But later, if you could stay on and answer the other ones in typing, then everybody will be able to see what the answers are.
Yeah, that's great.
And so the top two questions are, the first one has got 14 votes from Ida. Would you recommend that the reference screws should touch the brain tissue or only go into the skull without touching the brain?
That's a good question. I think I've seen both options, but to be honest, I don't know the difference. I think most of the applications I know they don't go through, but I think that depends on the lab. I don't know if one of you guys,
Nick, will you cover
Nick?
this?
I think it's going to work either way because the skull is electrically.
Yeah, I think so too.
To
yes.
Internal tissue, internal fluid. Yeah.
Okay, so we'll move on to the next question, which is from Alejandro. In your experience, is there a substantial difference in using dedicated internal reference sites versus using common average referencing across sites?
He's talking about the internal reference electrode?
Well, I mean, what you could do is take all the sites, do an average of all the sites, and consider that to, I think that's what he means, to be your reference.
Yeah, I think, maybe something I didn't mention regarding the internal reference electrode, and that will happen also with the averaging, is that you may cancel as well common LFP signal depending on how much of an average you do, and that happens also in the internal reference electrode. You will cancel out LFP signals that are closer to the internal electrode. So if your application is LFP, I think grounding can have also other difficulties because I think in the case of LFP, only having an external reference electrode is the best option. But I think averaging and using an internal electrode, that should be pretty similar for the rest.
Okay, thank you very much. Thank you so much to hear from the actual engineer who designed this. This is fantastic. There's lots of other interesting questions, like
I will have a look and I will.
Why are there grooves in the electrodes and sites and stuff like that? So if you answer in typing, that's great. Again, Carolina.
Okay.
Nick, you're on.
Let me just clarify one more thing about the referencing while we're here. Is that it's the internal referencing versus the common average referencing is not either or, it's and or, because because the common average referencing is applied post hoc in software, and you have to choose one of these referencing schemes that Carolina has described for your recording. So you can choose to apply the common average referencing or not. That's a decision you can make, and it's almost always useful to do so. But you're definitely going to have to choose one of these physical referencing schemes that Carolina described, just to be clear.